answers to the problems that I gave you on the Canvas. I don't know if it gave you a notification or not. If you haven't tried to do the problems yet, don't look at it. Try to do the problems yourself first, then look at the step-by-step answers that I so beautifully written out. Madison, how are you doing today? How's life in the hood?
Life is good. Mainly trying to motivate myself to actually do homework, but otherwise it's been good.
I tell you, it's really hard to stay motivated when you're not like going to campus. I know I couldn't imagine as a student, but even as an instructor, I'm getting lazier than, not that I was a workhorse to begin with, but even lazier.
Yeah, absolutely. And I think to some degree, like spring break made it worse because I got kind of used to not having to do stuff for spring break. And then now that we're back, I don't want to do work. I don't know. It's been a work in progress.
No, that is definitely and it's really bad like in for the fall because you got because Thanksgiving at Cal State, not at Fullerton College, but at Cal State, they got a whole week off. Then they come back after a whole week off. We only got 2 weeks of lecture left before final exam. I'm like, really? They're out of it now. They forgot everything. I'm like, I almost feel like Thanksgiving messes things up. Let's just finish it out, and you get a month off. But it's Thanksgiving, so. So, what we're going to do today is we'll talk about 4.3 again. I'll do another example from the homework. Then we're only going to do section 4.4, which is indeterminate forms, L'Hopital's rule. You'll know what that is when I go over it. And that's it. And then the section after that is actually 4.7. I know I put 4.5 down on the syllabus, but go with the homework sheet. And we can hold off on 4.7 until next week. So I want you to just make sure you learn 4.3 and 4.4 over the weekend really well, and then we'll start 4.7 on Tuesday. We should be good. Are there any questions in particular that you want to talk about from whether the test or the 4.3? If not, I will just pick one myself. All right, so let's see here. If I go back to the example, so all of these, I just posted this in the answer key section of your Canvas. So all 4 of these are done step by step, but please, if you haven't attempted, don't look at them yet. Try to do the problems yourself. How many of you at least attempted 1 or 2 of these already? Okay, Omar the Johnny, I see. Which is there a particular one that you already attempted that you want me to do?
We can try doing 3.
Okay, number 3. Have you attempted that one already? Okay. Ooh, that's a messy one. Number 13 from the book, which is like my number 4. Okay, we'll do that another time. You can look at it later. So let's do number 3 is hold on a second. Let me stop broadcasting for a second. It'll take a little bit of time. Okay. No, I will do number 2. 3 is a lot of number crunching, and you can look at that yourself. I already did it for you, but you can look that over the weekend yourself. You got to put in some time. I will do number 2 for you. The reason why I had to look at it for a second is because I actually did this for my last semester's class. So I haven't actually looked at it for a couple of months. So I want to see, yeah, number 3. Okay. Let's do number, I said, what number did I say I'll do for you? 2? Okay. Let me go back and sharing the screen. I forgot what number 2 was. It is x to the 4th minus 4x minus 1. All right, let me write a little bit better. All right, so here's what you're going to do. To find the relative extrema or the local extrema, you got to find the critical points. So you take the derivative, set it equal to 0. So cube root of x, cube root of 1 is 1. So you have your critical value of x equals 1. Now I'll do the second derivative test, because let's say I didn't ask you anything else. I just asked you for the local max / local min. I would do the second derivative test because it's so easy. Look at this. You just take the derivative of the derivative, which is the second derivative, and you get 12x squared, right? I just went from there to there. Then you plug in 1, and we get positive 12. It's a positive second derivative, so it means it's concave up, so you have minimum at the critical value. So the point 1 comma, whatever the y value is going to be a relative min. Now, what is the y value? You need that for display purposes, so you plug 1 into here to get the y value. 1 minus 4 is negative 3. Minus 1 is negative 4. So there is the answer for finding the relative max min right here. By the way, if I'm not seeing my paper right now because it's on the other page on my Notability. So if my answer of any of these differ from what I just put on Canvas for you, let me know. But don't look at it yet. Now, let's say I asked you over what intervals is it increasing or decreasing? So over which intervals is f of x increasing / decreasing? So we got to get the critical values, which we already did. It's x equals 1. And you pick a representative x value from each region, and you plug it into the first derivative, because the first derivative tells you if it's increasing or decreasing. So I'm going to pick x equals 0 to represent the side to the left. So you get -4, which is negative, so that means it's decreasing. Now I know it's got to be decreasing and increasing because I already know it's a relative min there, but I want to still do the work. So let's plug in x equals 2 for the right side. So 4 times 8 is 32, minus 4 is 28, so it's positive. So notice here it's decreasing on the left, increasing on the right. That's why it was a relative min. But also I can answer this question now. Say increasing on the interval 1 to infinity, decreasing on the interval -infinity to 1. So that's the answer for part B. And then part C, I ask you, is it, we're finding going for some inflection and concave up down. So for part C, you gotta find second derivatives, which is 12x squared. We already did it up there. So 12x squared, then equals 0. So x squared equals 0, x equals 0. Now, at x equals 0, we have a possible point of inflection. So what's the y value plus 0? Well, plus 0 is the original function, you get -1. So POI could possibly be 0, -1. Pi plus 0 is the original function. Now, I want to answer the question of which interval is concave up, which interval is concave down. And while I'm answering that question, I will confirm that it's one of inflection. So let's plug that value to the left 0, about -1. 12 times 1 is positive 12, so it's concave up. So it's concave up there, that's why the symbol concave. Now let's plug in a value to the right of 0. Positive 1. You'll notice you also get positive. Again, concave up. So it's concave up to the left and concave up to the right of 0. So it's never switched concavity. Therefore, the point at x equals 0, that's not a point of inflection. So the answer is we have no point of inflection and concave up on technically you're supposed to say -infinity to 0, union 0 to infinity. At 0 itself, it's technically like neither inflection. It's just neither. Because it's not at x equals 0. We don't have positive derivatives, so we can't call it concave up. So what happens, the graph is probably something like this. I'm just taking a guess, by the way. It's probably some situation where you have concave up, and it says never mind. So this would be the area where it's not concave up. Something like that, maybe. Where it would be, at that particular point, it's neither. Again, it's that graph, but you know what I mean. I don't know. It'd be interesting. I have to graph it to tell you. Actually, I have enough info to graph it here. Give me a second. I'd like to know the zeros. It's increasing then decreasing. Oh, I see what's going on. All right, anyway. Does that make sense? Let me confirm it here real quick. What I had here, I hope we have the correct answer. Yep, okay, same thing. Now, if you look at the other ones, the other problems 3 and 4 are more challenging. But again, I want you to try to do the problems yourself first. I don't want to just do them for you. They're there for you to look at later. Robert, what's so funny? All right. Anything else? Do you want me to show you the for number 13? Just to get the critical values, I'll show you that part, which is not like number 4 on my problems. I'll just show you how to get the critical values. Because if you know how to get the critical values, that gets you started for part A and B. And x is between 0 and 2 pi. So you take the derivative. What's the derivative of cosine? Minus sine. Set it equal to 0. And solve. Well, I'm going to move the cosine of x to the other side. When is sine equal to cosine? Just between 0 and 2 pi. Well, remember in the first quadrant, they're the same at 45 degrees, right? Sine and cosine are the same at the pi over 4, the 45-degree angle. So, but if you remember, there's 4 angles here, 4 where the reference angle is 45 degrees. But where is it where sine and cosine are both positive and they're both negative? That would be the first and third quadrant, right? Because in the second quadrant, sine is positive, but cosine is not. So they can't be equal. And in the fourth quadrant, cosine is positive, but sine is not, so they can't be equal. So, but in the first quadrant, they're both positive, and in the third quadrant, they're both negative. So therefore, x equaling pi over 4, sine of x is equal to cosine of x. And in the third quadrant, where the reference angle is pi over 4, so that would be 5 pi over 4. So those are your 2 critical values between 0 and 2 pi for, so once you know your critical values, that'll help you get your relative extrema, which would be pi over 4, comma, whatever the y value is, 5 pi over 4, comma, whatever the y value is. So you got to plug it back into the original. So you got to be familiar with your trig. By the way, those of you who are a little weak on the trig, make sure you learn it. And when you go to Math 152, you got to live and breathe trig. You need to be waking up hungover, being able to do trig. Like middle of the night, someone wakes you up. What's the sign of pi over 6? You got to say 1/2 without even thinking about it. All right. Are you ready to move on to the next section? Day, how are we doing over there? Good? Lauren, what city or state are we in today?
Still in Fullerton.
Oh, no Vegas, no Mexico, very boring Fullerton.
No.
Mhm.
But yeah, nothing so far. I'll let you know if anything comes up. Hopefully.
Okay, thank you. So let's start section 4.4. All right. Indeterminate forms and L'Hopital's rule. It's written as L apostrophe hospital, but don't read it like that. He's a French mathematician. If you say L hospital, your next professor will really give you the eye. It's L'Hopital. Although I cannot write L'Hopital and talk at the same time because in my head I have to say hospital to spell it correctly. But that's how it's written, L apostrophe hospital. But L'Hopital's rule. All right, so the main thing here first we're going to do is L'Hopital's rule. So that's the first thing item. So here it is. Okay. If limit as x approaches a of f of x over g of x is 0 over 0, or maybe any form of plus or minus infinity over plus or minus infinity. When I say plus or minus, meaning it could be infinity over infinity, negative infinity over positive infinity over negative infinity, any combination of infinity over infinity, or 0 over 0, then the limit as x approaches a of f of x over g of x is equal to limit as x approaches a of the derivative of the top divided by the derivative of the bottom. So go ahead and write this down and I'll explain in English. Basically, if you try to take the limit by plugging in the value that you're x as x approaching, if you get 0 over 0 or infinity over infinity, what you can do is take the derivative of the top, take the derivative of the bottom, and then try again. So let me explain. Let's do an example. Suppose I ask you a question. Example. Limit as x approaches 1 of the natural log of x divided by x minus 1. So notice if we try to plug in x equals 1, you get natural log of 1 over 1 minus 1, right? So that's 0 over 0. So since it's 0 over 0, L'Hopital's rule applies. Therefore, L'Hopital's rule applies. And only reason I'm writing that in red here because just to show you that's just for your notes. All right. So what we're going to do is we're going to take the derivative. Now, by taking the derivative, you're not using the quotient rule. You're treating the top and bottom as two separate things. You're taking the derivative of the top as it's its own problem, taking the derivative of the bottom as its own problem. This is the only time you do this. What's the derivative of ln of x? 1 over x. What's the derivative of x minus 1? 1. All right, now let's try to plug in 1. 1 over 1 over 1, so the answer is 1. That was the easy one, but as a first example, get you started. And that's L'Hôpital's rule, or a hospital. Don't say a hospital.
Professor, can you just explain again why you take the derivative of the top and the bottom separately? Is that just
Because
the...
that's what L'Hôpital's rule tells us to do.
Oh, okay. Okay, thank you.
Because it's f of x, you take the derivative of it, it's f prime of x. G of x, you take the derivative of it, it's g prime of x.
Thank you.
His name is not no, it's not that hard to pronounce. It's just you just pronounce it lo he tall. That's how you pronounce it. So, Madison, you specialize in this since you took German. So, like for example, like the German pronunciation of like Albert Einstein, right? Stein. That there's a lot of German last names, Stein. Like it's. I hate to use this guy as an example, but that's the only name that's thinking of. Weinstein. Isn't it supposed to be Weinstein? Weinstein? But for somehow when it becomes into English-speaking countries, they changed the Stein to Steen, huh?
Yeah, it should be Stein in German. Although I will say, like, German is nothing like French. German is honestly, the pronunciation is almost identical to English. So it's kind of easier to do that transition. Like French is obviously very different. But yeah, it would be
because English and German are sister languages, although they don't sound the same.
Right. Yeah, they're both Germanic languages. Yeah.
So, but if the last name is just Stein, in English we say Stein. But if it's like I knew a Goldstein, but it would be probably Goldstein if it was in German.
Yeah.
Let's do another example. Oh, so one other quick thing. So you know the company Volkswagen. I'm trying to blank. Okay. So I guess what's in German, the V stands pronounced like with like an F, right? Like Volkswagen. It's wagon of the folks. That's where it comes.
The V would be pronounced as an F, and the W would be pronounced as a V.
Yeah,
so it would be
yeah.
Volkswagen. Yeah.
It was started. It was as an economical car wagon for the folks. So Volkswagen. All right, next example. With 9. That's about how much German I know, Daniel.
Me too.
All right, so let's do this one. First, if you take the limit, first you got to see if you get 0 over 0, infinity over infinity. So if you take the limit as x goes to infinity, natural log of a number that's going towards infinity, yes, is infinity. Cube root of some number that's going towards infinity is infinity. So yes, we do have an infinity over infinity situation. So therefore, L'Hopital's rule does apply. So I'm going to rewrite this as ln of x over x to the 1/3. Now I'm going to take the derivative of the top, and I'm going to take the derivative of the bottom as if they're two separate. So the top is 1 over x. The bottom is 1/3 x to the negative 2/3. Now let's simplify this. I wrote my division like this. So 1/3 x to the negative 2/3 is the same as x to the 2/3 being on the bottom. Now, change that division to multiplication, invert the second fraction, and simplify. Then once you simplify, take the limit and see where you head. You want to try finishing this? So you got 1 over x times, you invert it. Now, remember your properties of exponents from algebra? If you if you're dividing two terms to the same base, you subtract the exponents, right? Now, I'm sure I'm writing every single little step here just so I don't throw anyone off, but you wouldn't have to write every single one of these lines. You could have went from here to here. So when you're dividing, you subtract the exponents. So it would be limit as x approaches infinity. 2/3 minus 1 is, because there's a 1 here, 2/3 minus 1 is negative 1/3. So this is really 3 over x to the 1/3, which is the cube root of x. Now we're ready to take the limit as x goes to infinity. As x gets really, really, really large without bound, the denominator is going to go towards infinity. So what's 3 divided by a really huge number?
0.
0.
Yeah.
Yes, that's it. After all that work, we got the answer 0. All right. Let me have you guys do one now. By the way, when you're doing problems in this section, feel free to use any technique that you learned previously in this class, like, hey, factor, multiply by the conjugate. So generally, the rule in the math is you can use stuff that you learned in previous classes or previous chapters, but not the stuff that you're supposed to see in a future chapter. All right, limit as x approaches 0 of sine of 4x over tangent of 4x. Tangent of 5x, I mean. Mark, I just saw your chat. Foxwog is, oh, that's how you pronounce it. I don't know. All right, let's go over this here. So if you plug in 0, you will get 0 over 0. You got that part at least? Okay. So we're going to take the derivative of the top and take the derivative of the bottom. So derivative of sine is cosine, and then the chain rule times the derivative of the inside, which derivative of 4x is 4. Derivative of tangent is secant squared times the derivative of the inside, which is 5. Now let's try to plug in 0. So if I plug in 0, I get 4 times cosine of 0, which is 1. The bottom, I get 5 times, well, secant is 1 over cosine. So cosine of 0 is 1. Square it, it's still 1. 1 over 1, so it's 1. So the answer is 4/5. That's pretty easy, right? You guys get that one? Okay. All right. So let's do one more here. Limit as x approaches infinity of x plus x squared over 1 minus 2x squared. Now, you could do this problem in 2 different ways. This is actually a pretty easy one. You can do it multiple ways. If you remember earlier in this semester, limit as x goes to infinity of a polynomial over a polynomial, if they're the same degree, you take the ratio of the leading coefficients. So what should the answer be? Without even doing any of the technique that I showed you right now. What's the ratio of the leading coefficient? 1 over -2. So the answer should be -1/2, no? As x goes to infinity of a polynomial over polynomial, since they're both x squareds, you take the ratio of the leading coefficient as 1/2. All right. Now, let's not do that. Let's practice our L'Hopital's rule. See if we get the same answer. But the answer better be -1/2, or otherwise something's wrong. The whole math universe falls apart then. So if you quote unquote plug in infinity, you do get an infinity over infinity. So, or infinity over negative infinity. It's still a combination of infinity over infinity. So you do, L'Hopital's rule does apply. And when you do that, you take the derivative of the top, you get 1 plus 2x over -4x. And then if you try to take the limit as x goes to infinity, you get infinity over negative infinity again. So L'Hopital's rule applies again. There you go. What's 2 over -4? I mean, like on a test, you could have done it either way as long as you stated. If you did it the first way, you just say, hey, it's polynomial over polynomial, so I took the ratio of the leading coefficients. And that would be perfectly fine. All right, let's do, before I talk about indeterminate form, let's do one more here.
Professor?
Yeah.
So when you have 1 plus 2x over -4x, we can break it down because it's still, you can still take the derivative of that still, right?
Yeah, because if you were to, the reason why we can still take the derivative, because I took the limit and I plugged in infinity, and I got infinity over negative infinity. So then again, you have to recheck to make sure L'Hopital's rule still applies. Then you can apply L'Hopital's rule again and take the derivative of the top, derivative of the bottom.
Okay, thank you.
Okay. You can't automatically keep using L'Hopital's rule. You have to do a recheck to make sure it applies again. 1 second here, you guys. Let me here. I look. Mm. All right, here's a good one. Okay, you guys do this one. Limit as x approaches 0, x times 3 to the x divided by 3 to the x minus 1. So when you do the homework, by the way, just real quick, I'll read the directions. Just find the limit. Use L'Hopital's rule where appropriate. If there is a more elementary method, consider using it. What they mean by that is what we did previously. I don't know if elementary would be the correct word, but you know, what we did in the previous chapters. In math, when they say a more elementary method, like if you become a math major and you do much more advanced math, then they would call all of the stuff in this book elementary method. So it's all relative. How many of you are done, by the way? Oh, Addison, you private message me the answer. Don't give it away to other people who are still working on it. Well, how many of you are done? Are most of you done? Or most of you are not even trying. You're just looking at the screen, trying to see what's the next joke that I'm going to say. Does anyone have a good joke, by the way? Classroom appropriate, so I don't get fired. No, that's correct. I think. All right, I don't know if I told you this joke. Here we go. There are 3 types of mathematicians: those who can count and those who can't. Okay, let's go over this. So if you plug in 0, you get, let's see here, 0 times 3 to the 0 over. So 0 over 1 minus 1, which is 0 over 0. All right, so L'Hopital's rule applies. So now we're going to take the limit as x approaches 0. Let's do that in black. And you'll see a lot of times the book, if you look at like how the book does it, they'll put a capital H over the equal sign. You don't have to. You could, if you're just saying we're going to use L'Hopital's rule. That's why this is equal to that. So first, we got to use the product rule upstairs times the derivative of the second plus second times the derivative of the first. All over the bottom, derivative of 3 to the x is 3 to the x ln 3. Now let's try to plug in 0. So we get 0 times 3 to the 0 ln 3 plus 3 to the 0. All over 3 to the 0 ln 3. So now 0 times anything is 0. So this whole thing gets cleared out. So we just have 3 to the 0, which is 1. And that's 1 as well. So 1 times natural log of 3. So 1 over ln of 3. And please just leave your answer as 1 over ln of 3. Do not take out your calculator and say, oh, natural log of 3. Let's see what that is. Because he said the exact answer. So 1.09. No, that is not the exact answer. That's an approximation. 1 over natural log of 3 is the exact answer. In fact, one time I said no calculators. So someone used a calculator and they put 1.0, that's it. They put whatever 1.09861228.9. And then I go, I told you no calculators. They're like, I didn't use a calculator. I go, how the heck did you get 1.26, 7, 8, 9, 10, 11, 12 then? Sorry, I'm a little intense. Moving on. All right, before I give you a break, let's do a math trick. Did I do that math trick where I add a bunch of numbers together for you? All right, let's do this here. Madison, can you give me a random 5-digit number? Oh, your mom probably already did this trick for you. Never mind, you're out of here. Rachel, give me a random 5-digit number. What I mean by random 5-digit number, don't say like 22222. They're like random, mix them up, makes it harder on me. Go ahead. You can just verbally say it.
74392.
All right, there we go. That's random. Now, someone else, have you seen this before, Madison?
I have not, no.
Okay, give me a random 5-digit number.
63754.
All right, let's go. Who else wants to volunteer to give me a random 5-digit number? Whoa, this is tough. All right, Lauren from Fullerton, go ahead.
24987.
All right, since this is tough for you guys, I'll do the rest myself. 3, 6, 2, 4, 5, 7, 5, I don't know, 0, 1, 2. All right, here we go. So you got 5-digit numbers right now. If I was doing this in the classroom, it would be more impressive. I'm no longer looking at it. I'm just looking at you guys, okay? So, okay, I'll look up in the ceiling there. So you can see I'm not looking at it. Now, I'm going to quickly add this. You can use your calculator, and I'm going to go left to right. You learned in elementary school adding right to left. I'm going to go left to right, right here. Go ahead, you can start. Done. See how fast that was? 274, 390. All right. Do you want to check it?
It's right.
All right, so Daniel, you've seen this before, no?
Oh, I'm actually kind of surprised right now.
All right, I'll show you how it's done. It's actually just like any math trick or any trick. If you know how to do the trick, how it's done, then it's not as impressive. So the first 3 numbers you guys picked, right? They were random. The last two, I made the excuse that you guys are going too slow, so I'll do it myself. The last two rows were not random. So I picked these numbers and I corresponded it with this row. So notice that the 6 and the 3 here add up to 9. The 3 and the 6 add up to 9. 7 and 2 add up to 9. 5 and 4 add up to 9. 4 and 5 add up to 9, right? Then what I did is I picked the numbers in this row specifically to correspond with this row. So notice here, the 2 plus 7 add up to 9. 4 and 5 add up to 9. 9 and 0 add up to 9. 8 and 1 add up to 9. And 2 and 7 add up to 9. So each of those columns add up to 9. So the two blue rows add up to 99,999. Let's just call it 100,000. And the two orange rows also add up to 100,000. So 100,000 plus 100,000 is 200,000. We're two less than that, but let's just call it 200,000. So how do you add 200,000 with plus that top number 74,392? So all I did is I put a 2 here, then I recopied this number 74390, but I took 2 off at the end because it's 2 less than that. So all I was doing is writing a 2 down and I recopied that top number, but subtract 2 at the end because you're 2 less than that. That's it. All right, so next time you're at a party, you can do this. We'll take a 10-minute break. We'll start back at 4:20. Oh my. All right. Let's get started. Oh, one more minute, sorry, till 4:20. Cole, how are we doing? What's your major, by the way?
Yeah, it's currently undecided,
Oh,
but leaning towards computer science and more recently, actually, mathematics.
yeah, math. Computer science, what are you going to sit behind a computer, do programming all day, boring, and make lots of money? Math, you more enjoyment.
Get to tell jokes or tricks.
You have other math teachers that joke around, or am I the only one?
No, not even close. You're like the only one. It's pretty cool.
Okay, let's get started. So we're going to talk about indeterminate forms. What indeterminate forms is pretty cool is, you know, when you multiply a number by 0, it's always 0, right? Like 5 times 0, the answer is 0. 6 times 0 is 0. You know, 500 times 0 is 0. Any number times 0 is 0. Now, anything times infinity is infinity, right? 5 times infinity is infinity. 6 times infinity is infinity. Any number times infinity is infinity. So what happens is, what if like these two superpowers collide? 0 times infinity, what happens now? Because anything times 0, 0 wins out. Anything times infinity, infinity wins out. Well, what happens when these two collide? The answer is it depends. Depends on what the functions are, what the situation is. Sometimes it's 0, sometimes it's infinity, sometimes the answer is some number in the middle, like 17 or whatever. So that's what we're going to do. Now, before I get to that 0 times infinity scenarios, when you have a situation like that, you can always write, suppose you have limit as x approaches a of f of x times g of x, where, like, let's say one of them is going towards 0, one of them is going to infinity. So without the loss of generality, let's call f of x is the one that's going towards 0, and let's say g of x is the one that's going towards infinity or negative infinity, it doesn't matter. If that's the case, we could write f times g as f divided by 1 over g, or g divided by 1 over f. Now, how is that possible? Well, it's a little easier to explain from here to here. So, just FYI, I'll show you here. If you have f divided by 1 over g, isn't that the same as f times g over 1, which would be f times g? But we're going back. Now why do I want to write something as nice, f times g as f divided by 1 over g? Well, remember, if you have a 0 times infinity scenario, what we're trying to do is write it as a fraction, where if you have infinity and you write it as a fraction, it's 1 over infinity becomes 0. So then you're making it 0 times infinity becomes 0 over 0. The whole point of going from this to this is you're trying to make 0 times infinity look like it's 0 over 0. So you use L'Hopital's rule. That's why you switch. That's why we would write 0 times infinity like this, so it becomes 0 over 0 or infinity over infinity. So let's do an example. Hopefully this will make more sense. And let's do this one. Limit as x approaches negative infinity of x squared times e to the x. So because limit as x goes to negative infinity of that. Notice how this is 0 times. Let's see. If I were to plug in, not take the limit as x goes to negative infinity. You see how x squared will go towards infinity because negative infinity squared goes to infinity. But e to the x, when you plug in negative infinity, would that be 1 over e to the infinity? Because e to the negative infinity is 1 over e to the infinity, which would be 1 over e to the 0. So we have infinity times 0 situation here. So what we're going to do is we're going to draw 1 over the denominator and rewrite it as the limit as x approaches negative infinity of x squared divided by 1 over e to the x. And that's kind of like what I highlighted in orange up there. So now notice what that does when you do that. If you were to take the limit as x approaches negative infinity, now x squared, that still goes to infinity, but look at 1 over e to the x. That ends up going, that ends up being 1 over e to the negative infinity, which is e to the infinity, which is infinity. So you have an infinity over infinity situation. So I made a 0 times infinity an infinity over infinity situation. So therefore we can use L'Hopital's rule. That's basically what you're doing when you have a 0 times infinity situation. You're making it as a fraction, so you can use L'Hopital's rule. So I'm rewriting it like this now, so that it's easy to take the derivative of. Now we're going to use L'Hopital's rule and take the derivative of the top and the derivative of the bottom. Derivative of the top is 2x. Derivative of the bottom is itself, because it's e to the negative x times the negative 1. Now, let's quote unquote try to plug in infinity. Let's see here. If I take the limit as x goes to negative infinity, 2x will go to negative infinity. Negative e to the minus x, let's see, that will go to negative e to the infinity, which is negative infinity. So L'Hopital's rule applies again, because you got an infinity over infinity again. So let's take the derivative of the top, which is 2. The derivative of the bottom, e to the minus x, is itself times negative 1, so the negatives cancel out. All right. Now I know we're not going to get infinity over infinity or 0 over 0, because I know the top is going to be 2. So it's going to be 2 over something. So it's going to be 2 over e to the negative infinity, which would be 2 over e to the infinity, which would be 2 over a very huge number, which is 0. In this case, 0 won out. The answer was 0. Now, having said that, I'm not going to give you a 0 times infinity type situation for a test or a quiz, but I wanted you to do an example just so you can see it and just touch up on it. When you're doing the homework, if you look at your homework sheet on 4.4, I said do 9 through 23, 31 through 35, and then I said 45 to 47. So the 45 and 47 are the ones that's the 0 times infinity. So don't stress about these. Make sure you focus on this right here. So the 45 and 47, don't stress about it. But that's the 0 times infinity situation. Anyway, so I'm kind of done. I just wanted to make sure you do 4-3 if you haven't done it so already, and 4-4. And then the 4-3, the problems that I gave you, the problems are on the answers are on Canvas. And then that's about it. Do you guys have anything for me? Oh, we got to take a quiz. No, I'm just joking. We're not taking. I didn't say we're gonna have a quiz today. I almost gave Damaris a heart attack. I'm just. All right. Well, stick around if you want to talk. Otherwise, Madison, did I forget anything?
No, I don't think so.
Oh, all right. Anyway, yeah, I'll see you guys next weekend, huh? Have a good weekend.